Okay, good morning. So I continue our discussion about matrix theory, but mainly I want to give you some problems to work on those problems yourself, and then after a while I will come back and try to solve those problems for you, okay? So if you remember last time we actually talked a little bit about this theorem. And actually this theorem tells you that if A and B are commuting matrices. Of course, commuting matrices should also be square matrices, otherwise they don't commute at all. Uh, so if A and B are commuting square matrices of the same order, then for every non-negative integers m and n, any power, any integer, positive integer power of A commutes with any positive integer power of the other one. Okay, so this is not trivial, because if I have a matrix A and if I raise it to some power, it becomes probably a totally different matrix, yes? So there is no guarantee that if I know something about commutativity of A and B, this will be inherited to any powers of A and B. Okay, because A to the m and B to the n are essentially totally different matrices with respect to their origins A and B. Okay, so how can we show that? We can do this in this form. We can say that if A commutes with B, meaning that this happens, we want to show that A to the power A times B to power n also commutes with A, and B to the n also commute, meaning that A times B to the n is equal to B to the n times A. That is my question mark for all non-negative integers n. Yes? So this is, if you want to do it formally, you have to do it using mathematical induction, yes? So we say that, okay, if n is equal to 1, so my goal is to prove this equality based on this assumption, yes? So if n is equal to 1, then I will get ab to the 1 is equal to b1 to the a, but this is true, yes? Based on the assumption that I have for matrices A and B. Now we assume that this is valid for k, meaning that A times B to the k is equal to B to the k times A, assumed to be true. Of course, here k is any natural number greater than or equal to 1. And then we want to show that the next one is also true. We want to show that A times B to the k plus 1 is equal to B to the k plus 1 times A. We want to show this. Okay, what I can do, I can start from the left hand side. For example, here I would say the left hand side is equal to, instead of A, B to the k plus 1, what can I write? I can write A, instead of B to the k plus 1, I can write B to the k multiplied by B, based on the definition of the power of a matrix, yes? And because of associativity, I can take the pair of brackets from the second pair and put them around the first pair. So it becomes A, B, K, and then I have B alone. Now I can use this assumption, yes? We know that A times B to the k is assumed to be B to the k times A. So instead of this one, what I can write B to the k times A and multiplied by B. But again, using associativity, I can put the pair of brackets around the second pair, And then again, I can use the assumption in the beginning of the problem that AB is equal to BA. So I can write BA here instead of AB. And again, I use associativity. So it becomes B to the K B times A. And now B to the K times B is nothing except B to the power of K plus 1 times A. And that's exactly equal to the right hand side. So you see, you have to play around with these associativity quite a lot here to be able to show that this is indeed correct. So what I have shown is that, of course, you can read it in English, yes, you don't need to use letters here. So you can say that if I have two matrices that are commuting, any power, any non-negative integer power of one of them commutes with the other one. So I'm not referring to any particular matrix called A or B. I'm just translating this in an English sentence. So it would be, if I know that two matrices are commuting, I was able to show that any non-negative power of one of them commutes with the other one. So this is the take on from this proof in general. So this is the reason that I am telling it in this way, because I do not want to use another mathematical induction, because here you see this power and this power are different. Here I have chosen power m equal to 1, but this is in principle should be done for any power. So I would say that when you say for the second part, I would say that when you tell me that AB is equal to BA, I can conclude that A B to the n is equal to B to the n A. This is what I just showed, yes? Okay, and then we can do something like this. Let me call this capital B, or I don't know, curly B, yes? Okay, now don't look here, look here. You have a matrix A which commutes with this curly B. So this tells you that this curly B should commute with any power of A, including the mth power, yes? So this implies that A to the m commutes with this curly B. Because of that way of reading it, do you remember I read it in English? So this gives me this. And then instead of curly B, I replace the normal B to the n. So it becomes A to the m, B to the n is equal to B to the n, A to the m. Okay, so that is extremely important, because I told you that usually it's very important to know which matrices commute, because this is the only non-trivial operation in matrix theory. So it is very important that to know by heart that for which matrices we can do this commuting, we can do this interchange, and for which one of them we cannot do. Okay, because you know that if you can commute, you can solve the problem easily. The commutativity is gone in general, but whenever I can apply it in particular cases, it is very helpful. So it is good to have a systematic category in your mind for commuting matrices. So this is one of them. Any questions? Let us go to the next theorem. So if you remember, we talked a little bit about powers, and then we learned that, for example, if A is a number, we know that A to power m times A to power n is equal to A to power m plus n if m and n are non-negative integers, okay? And then we also learned that if A is a square matrix, the same is also true for matrices, matrix A, yes? You can write A to the power of m plus n. So we can say that matrices inherit this property of numbers, yes? And then we also had, if a is a number, we have a to the power of m to the power of n is equal to a to the power of m times n. We also learned that this is also true for matrix A. A square matrix can be, enjoys the same property. But of course, for numbers, we know that if I multiply two numbers and then I raise it to power n, it becomes exactly equal to a to the n, b to the n. And then we talked a little bit about that this is not expected, at least, to be true in general for matrices A and B. And the reason is that. So the reason is that if you want, for example, to prove this, let us see how the proof of this for numbers work. If you want to prove this for numbers, you start from the left-hand side. You would say that a times b to power 2 means ab times ab. Yes? But now, when we were dealing with a and b as numbers, we know that we can interchange these two because a number multiplication is commutative. Yes? So it becomes a instead of b. At first, I use associativity to put the pair of brackets around the middle pair, and then in the middle pair I would write AB because there is no difference between BA and AB if A and B are numbers, and then you can use associativity, put a pair of brackets around the first pair, put a pair of brackets around the second one, and then of course A times A is nothing except A squared, and the second one is B squared. Yes? So this is, and this becomes the right hand side. So you see, when you want to reach from the left hand side to the right hand side for numbers A and B, what properties we are using? One property is associativity, and the one property that I used here is commutativity, and again associativity. Okay, but anyway, I have to use commutativity. But we know that for matrices A and B, in general, this is not true, that A and B commute, so we might get suspicious about that might be this is not true in the first place, and then actually it is not. I don't know, we can cook up some examples to show that this is indeed not correct. So you can give yourself examples. Yes, you can, I don't know, make, usually most of the time, if you start with two non-commuting matrices and let us take n equal to 2, you calculate the product and then raise it to power 2, and once you calculate each one of these second powers and then multiply them, and you will see that they are not equal. But of course you see that if A and B are commuting matrices, this is indeed true. Yes? So let me just get rid of this, we don't need that one, to save some space. Now we want to show that if you want the same formula, which is valid for numbers, to be valid for matrices as well, there is a condition that should be met first, and the matrices should be commuting. Okay, in that case, yes, you're allowed to use this formula. Okay, if I want to prove this, again I have to use mathematical induction. Okay, so let us just do this. If I put n equal to 1, then the left hand side becomes ab to power 1, the right hand side becomes a1 b1, but this is completely equivalent to saying ab is equal to ab, and then we know that ab equals to ab is true. Now let us assume that this is true for k, so it means that I know that this holds, assumed to be true. And then we want to show that this is also true for the next step. So I want to show that this is equal to a to the k plus 1, b to the k plus 1. Okay, so this is something I want to show. So what I do, I start from the left hand side. I would write ab to the power of k plus 1, but what is the meaning of ab to the power of k plus 1? I want to somehow be able to use my assumption, and in my assumption you see that the power of k is involved, so it is motivating to write this in this form. Yes. or might be you choose to put k here and 1 here. In principle, it shouldn't matter, okay? But this one, according to the assumption, according to the hypothesis of this induction, this should be equal to a to the k, b to the k. So it becomes a to the k, b to the k, and then I have ab. Okay, then what should I do? I can use associativity to put a pair of brackets, these pairs of brackets around the middle pair. Okay, now can you tell me how should I continue and why?
You switch the k and
Why can I do that?
because they're commuting.
Because what?
They're commuting. Because of the previous law.
Because of the previous theorem, yes. Yes, you are right. A and B are commuting, but A and B are commuting. We don't know that A and B to the k is commuting in the first place unless we have already convinced ourselves that this is indeed the case, and we did it. We showed that if two matrices are commuting, any power of the one of them is commuting with any power of the other one. I mean non-negative integer powers. Okay, so yes, this is inevitable. You have to use this theorem. It's not, I mean, I want you to understand that just because of this assumption, it is not trivial to conclude that you can interchange these two unless you have already shown the validity of this operation. Now, yes, so I would say b to the k times a is a b to the k. I would write previous theorem. Okay, now we can continue. So then everything becomes very simple. So I would write a b to the k, and then I can write b, and then I use associativity to put the pair of brackets around the first and around the second pair. But you know that a k to a is a to the k plus 1, and the other one is b k plus 1, and this is indeed equal to the right hand side. Okay, I think this is trivial, but these are things, by the way, we shouldn't call it trivial. Even if the proof is simple, you shouldn't call it trivial, you should say it's straightforward, so it's not hard. Okay, now I want to look at these equalities here. Which of the following equalities in general is in general true? All matrices are assumed to be square matrices of the same order. So this word in general is important for me. Okay, so for example, if this is not a matrix, assume that A and B are not matrices, they are numbers. Let me write and I clean it. If I tell you what is A to the 3 times A plus B to the 3, assume that these are just numbers. Okay, we know that I can write A times A plus B to the 3, yes? I hope that you don't have any doubt for doing this when you are doing simple algebra in numbers. And then if I multiply A in the pair of brackets, it becomes A squared plus AB to the 3. Now what I'm trying to see, you see what I have written here, I want to draw your attention to it. That's it. That's not a very tricky problem. I want to see that, you see what I have written is this one and that one here, but instead of A and B as numbers, I have written them as matrices. Now I'm asking you, do you think this equality is in general true or not? And I want you to think about this, and that, and then answer me. I hope the question is clear. Otherwise, please let me know.
I think no, because we haven't proven this moving the power of the x for
No, we do. So we talked about this. Everything about removing the powers and putting one single power is done. Now, based on your knowledge, you need to give me an answer for this problem. You said in general no, and I agree with you, but why?
No, because we can't prove it for matrices.
Okay, but what? But why? So let me tell you another thing. What assumption? So your answer is correct. You say that no, we cannot do that. Okay, let us talk about the other one. What do you think about the other one? Do you think the answer to all of them is no? Because all of them are using this rule somehow. But from the right hand side to the left hand side. I am using this rule for all of them. So do you think that there is a big no for all of them, or some of them might still be true? That's my question.
There's an exception for like even numbers and
No, I don't think even an odd play any role. The parity of that number doesn't play any role.
then I'd say no for all of them.
Okay. What about others?
Well, I don't think we talked about the matrix distributivity, so I would also guess no.
No, we talked about that. Remember,
Okay.
associativity, distributivity, these are preserved. The only thing we lose when we go to matrix theory is commutativity. It's extremely important, be careful, that there is only one single property that we lose, and that is commutativity. Any other opinions? I would say that the first one is not in general true, so you were right. One, this equality is not in general true. Okay, can you complete it for me again? Unless I'm giving you another chance. Unless what happens? Unless it is mentioned that, unless we know that. Okay, can you complete what I am going to write?
Unless we know that A and A plus B commute.
Thank you, yes. So let me write this in pair of brackets. Unless we know that this pair of matrices involved, A and A plus B, commute. Which we don't know, because I told you that whenever it is not mentioned in the problem, the default mode is to consider that the matrices are not commuting unless you have a good reason from your previous knowledge and what you learned about matrices that yes, they are commuting, or it is explicitly mentioned in the problem that's commuting. So we don't know that they are commuting or not. So it means the default mode is that I cannot assume that they are commuting. There is no reason that A and A plus B commute. So let me just be a little bit more careful here. So if I want to say A and A plus B commute, what does it mean? It means that I need to convince myself, is it true or not? But let me simplify this. Distributivity gives me A squared plus AB. Yes. This one, distributivity from right, gives me A squared plus BA. Of course, there is a common part here, A squared. But you see, in order this equality to hold, this means that this part is of course the same part here, no problems, but I need to know that AB is equal to BA, but I don't know. I don't have any guarantee for that. There's nothing extra information in the problem saying that AB is equal to BA. So exactly what you said is correct. we cannot assume that A and A plus B commute, and then this theorem is valid when A and B are commuting matrices. So I am not allowed to use this simple rule that was correct for numbers. Okay? But I just want you to know that the solution to this problem here is no, and if someone asks you why, you would say because the matrices involved are A and A plus B and they do not commute in general. Okay, now can you tell me what happens for the next one? For the next one, it's comparable with this property. So let me write and then I will clean it, okay? So if I give you number A to the 4, these are numbers now. Instead of 2i, I would write 2, and then I would write A, and then I would write to the 4. Okay, if I am working with numbers, then I can write a power of 4 here, and then I can multiply these two, and then distribution tells me that this becomes 2a minus a squared. And this 2a minus a squared is exactly what I have put here, and so this is this relation. I want you to understand the differences of this algebra, so don't think that because you can do this in numbers, automatically this is guaranteed that you can also do this with matrices, unless you have a good reason for that. Okay, now tell me, do you think in this case, do you think this is true or false, and why?
It is false because we cannot guarantee that A commutes 2i minus a.
What about others?
I think it should be true
What?
because the identity matrix should commute with any other matrix of the same order.
But we're not comparing A with I, we're comparing A with I minus A.
Yes, yeah, you are completely correct. What we are comparing A and 2i minus a. Yes, everybody agrees? We have to compare A. If I ask you what are the numbers involved here, you would say one number is A, the other number is 2 minus A. If I ask you the same question here, you would say that the matrices involved are A and 2i minus A. So if I can use this if I know that these two matrices commute. Okay? So I think it's very you shouldn't be in hurry and jump into this conclusion that because A commutes with I, it commutes with the combination. You need to check it, okay? And when you check it, accidentally it turns out to be true. So I would say that, so Alexander Björkman actually answered correctly, but draw the wrong conclusion. Yeah, so this turns out to be true, but you are right. We have to check the validity of the commutativity of A with 2i minus I, 2i minus A. So what does it mean? It means that I need to ask this question from myself. Is there any guarantee that this matrix is equal to that? So don't be in a hurry to draw some conclusions, yes? If the answer to this is correct, is positive, it means that these two matrices are commuting, then I am allowed to use that rule and this becomes true. If not, no. So, but let me check. If I want to check this one, I will check the left-hand side. What is the left-hand side? I start using distribution to multiply here, there. It becomes 2a minus a squared. Agree? This is the left-hand side. If I calculate the right-hand side, I have to use distribution but from the right. But it doesn't matter because a times I was a. I times a is also a. And a times a in any direction is a squared. So then it becomes 2a minus a squared again. So they are indeed equal. So it means that the matrices involved are commuting, so then I can conclude that yes, a to the 4, 2I minus a to the 4 can be written as a times 2I minus a totally to power 4, and then I multiply a inside, so it becomes 2a minus a squared to the power of 4. So I would say that, so 2 is true, yes? Is that understandable? I'm just trying to draw your attention to these very simple and very important points, because if you don't value these things, you will be in trouble when you deal with matrices. Okay, what do you think about the last one? Okay, sorry. Yeah, I can make it a little bit smaller. I think we do not have enough space, so let me make some space while you are thinking. Okay, now what do you think about number 3? Do you think it is correct? Is it true or false? Any opinions?
I'm still kind of listening. I think it should be true.
Yes, can you elaborate a little bit more?
It's basically the same thought process as the previous one. We split a to the power of 8 into a to the power of 3 times a to the power of 5.
Yeah, exactly. So let me do it step by step. So let me come with you. So yes, you are right. The first thing that we do, I start from the left hand side. As you said, instead of a to the power of 8, I write a to the power of 3 multiplied by a to the power of 5, because one of the rules. This is the famous rule of powers, which is always true for matrices as well. And then, as you said, so let me, okay, then what? Can you tell me now?
Then we have to check
Mm-hmm.
if a and 2a squared plus a cubed plus I is commutative.
Exactly. So we need to check, because now there is a common power here. I want to put the power here and multiply these two matrices. If I ask you what are the matrices involved in this problem, you would say one of them is A, the other one is this combination. But you shouldn't be in a hurry and jump to this conclusion. There is no guarantee that these matrices are commuting because it's not mentioned. There are some exceptions that you have already studied about them, so you are right. We need to check the validity of this commutation relation. But then I think you immediately realize that this is indeed true. If I ask you what is this one, you use distribution and you say that a to the 3 plus a to the 4. A times I, a on the left, I on the right, it becomes a. But then on the right hand side, I have to multiply from the right. But it doesn't matter, because here you multiply a by a squared, it becomes a cubed. Here when you distribute, a squared is on the left and you still multiply by a. Again, this becomes a cubed. Okay, so this becomes 2a cubed and then a to the 4. I times a is also a, and then this becomes true. You see, they are exactly identical. 2a cubed plus a to the 4 plus a on the left, the same expression on the right, so they are the same. And then you are allowed to use that. So I keep a to the 3 and I use this theorem and to write it in this form. and then I put the power of 5 up there, and then again I use distribution to multiply that, so it becomes 2a cubed plus a to the 4 plus a, and then finally to the power of 4, and that is the right hand side. So you see, we were able to show that this is valid for in general. I don't need any extra piece of information for the matrix A. Okay, so I'm not saying that these are important problems, but these are important points that you should appreciate when you are working with matrices. Another thing that I want to say, and then I will give you some exercises. I want you to think about them first yourself, and then if we have time I will come back and guide you through them. Otherwise we will solve them next week, and I think it would be better to work on those problems yourself. One other thing is that you know that identities are very handy tools. Yes. For example, if I want to calculate something here, instead of multiplying 3 times, I immediately used an identity and facilitate my job. You know, I can do it faster. It would be great if I can take these identities to matrix theory as well. But I hope that you immediately agree with me. Unfortunately, there is no guarantee for that. Yes? Because, for example, let us consider, for saving some time, instead of the cubic identity, let me use the squaring one. So, y a plus b, I will write and then clean it because these are very simple things. Y, if a and b are numbers, we know that this becomes the first one to the 2, 2 times the first one, times the second one, and the second one to the 2. Why we should doubt about this identity to be valid when a and b are matrices instead of numbers? The reason is that if you want to prove this, you have to use commutativity. At least you need to know that a and b involved in this particular problem are commuting, and it's guaranteed for numbers, because if I want to prove this, I would write this multiplied by itself, and then I start distributing this. It becomes a squared plus ab, and then when it come to b, I have to write b times a, and then b squared. But for numbers, there is no difference between ab and ba, so I can combine them and write 2ab plus b squared. So immediately it becomes evident that if I have a and b and I want to square it, if I naively write a squared plus 2a times b plus b squared, I might be completely wrong. The reason is that there is no guarantee that matrices a and b commute. So it means that at most what I can write for this is a squared plus ab plus ba plus b squared. Nothing more, unless there is a good reason that I am guaranteed that a, b, and ba are equal when a and b are matrices, which in principle I don't know. But the strategy becomes exactly the same. Now, do you think this identity is correct? You see that I am using the same identity for a and 3i, and I am writing the first one to the 3, 3 times the first one to the 2, times the second one. I am following this rule. 3 times the first one times the second one to the 2, and finally the second one to the 3. Do you think that this is valid? Yes? What are the matrices involved here? One of them is A, one of them is 3 times the identity matrix. But you know that A commutes with a multiple of the identity matrix. So yes, even though this formula in general is not true if A and B are matrices, but if A is going to play the role of this one and 3i is going to play the role of this one, because A and 3i are commuting, so it is guaranteed that what I have written here is completely valid. Do you understand what is going on? Yes? So it means that if you want to use algebraic identities, you have to be very careful that all matrices involved are commuting. If all matrices involved are commuting, then you can use exactly the algebraic identities. Even you can use, for example, Newton's binomial theorem. So for example, you can write a plus b to the n is equal to the sigma, as we learned in Math 5, choose nk, and then you can write a to the n minus kb to the k. So that formula is valid, but there is a big if there, and that if is that if a and b are commuting. So as far as you know, the matrices involved are commuting, mutually commuting. If there are three matrices, A, B, and C, it's not enough to guarantee that A and B commute. You have to check that A and B commute, A and C commute, and B and C commute. If you are guaranteed that all these three pairs commute, then for example you can use any algebraic identity involving three matrices A and B and C. For example, if you want to raise them to power 2, I don't know if you have followed my lectures last year, this mathematics inspiration or what, we learned that an identity a plus b plus c to the 2 is equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc, if you remember. So is this identity valid also if a, b, and c are matrices? If it is going to work, I have to check three pairs of commutativity. A with B, A with C, and B and C. If this is the case, yes, you are allowed to use this even for matrices. So this is the crucial point. You see that we are just losing commutativity, but it brings you a lot of unexpected results that you have to be careful. Otherwise, you will make mistakes, and that would be troublesome if you want to work with matrices. Any questions so far? Okay, good. Yes? Is it clear? Okay. Now let me just show you a page here. I have written these examples 2, 3, 4, 5. It might be they are a little bit challenging. I don't know. They are not that challenging, but it depends how much experienced you are in matrix theory. So there are 4 problems here. That would be great if you can take a screenshot from this so that I can also work on the lecture notes for Math 5 while you are working here. There are some minor things that I want to fix there. So yes, try to think about these problems and try to solve as much as possible. And then if you have forgotten, the example number 3, I have written let A be an idempotent matrix. Any one of you remember what was the notion of an idempotent matrix?
That whenever it is multiplied by itself, it becomes the same.
Yes, so A squared is equal to A itself. In that case, that becomes idempotent. Yes. So try to solve these problems, work on these. Let us see how it goes. And please take a screenshot because I want to pause the video and take share the screen away. Do you have the screenshot now?
Yes.
Everyone, yes?
Yes.
Okay, thank you. So let me just pause the video. I don't know if we have enough time to come back and solve it together. Let us start at least making sure that you are on the right track. So can you give me your opinion about this example number 2? So how did you go from a squared to a to the 5 to show that this is also true?
I split a to the 5 up to a squared times a squared times a.
Yes.
And then instead of the a squared, I used the identity of
Yeah.
a squared equals a.
Yeah, that's completely right. That works. But if you don't mind, let me do it in a little bit different way. But of course, the idea is exactly the same as you did. So here, what I do like this. I would say that a squared is equal to 2a minus 3i. I know that my goal is to reach to a to the 5, so let me raise both sides to power 2. So then it gives me 2a minus 3i squared. The left hand side of course becomes a to the 4, and the right hand side, tell me, can I use any algebraic identity for the right hand side? To be specific, can I use a squaring pattern for the right hand side? If yes, why? What is the point that you need to care if you want to answer this question? I am asking you, can I use this formula?
Yes, because A and I commute.
Because 2a and 3i commute. Exactly. So I am on the safe side if I want to use the formula. So it becomes the first one to the 2, 2 times the first one times the second one, and the second one to the 2. But I squared is just I, yes? Okay, but then this is the way that I usually do these kinds of problems. You see that now a squared appears. I reduce the degree by invoking this once more. So what I do, I would write 4, instead of a squared, I put 2a minus 3i, and then I have minus 12a plus 9i. Yes, and I simplify that. It becomes 8a minus 12i minus 12a plus 9i. But before continuing any further, I can simplify a little bit more. So it becomes minus 4a, because 8a minus 12a is minus 4a. And then I have minus 3i. So then this, if I want, I can write it as a to the 4 is minus 4a minus 3i. But I'm not finished yet because I need a to the power of 5. Okay. As you said, Alex, so here I multiply by a. It is exactly what you said. You said that you split a5 to a2, a2, and then 1a. But instead of a2, a2, I wrote a2 to the 2 and then multiplied by an a. So I'm now doing exactly your strategy. So I multiply both sides by a. The left-hand side becomes a to the 5. The right-hand side becomes minus 4a times a is a squared. And then minus 3a times I is nothing except 3a. But again, this is correct, but this is not the demanded form in the problem. So it is clear that instead of this a squared that appears right now, I can again do this substitution. So this becomes minus 4 2a minus 3i, and then I have minus 3a. So then I do the simplification once more. So it becomes minus 8a plus 12i. I hope that I have done everything right. Yes. Yes, it is correct. So it becomes 12i and minus 11a. So this means that finally I got a5 to be 12i minus 11a, and that is exactly what is demanded in the prop. Good. So you see, these problems can also be somehow fun, you know. Okay. Is any one of you have solved number 3?
Yes.
Okay. Anyone else? Good. Who one else? Okay, now let me, Alex, this time, Björkman, ask you your opinion this time. So how did you solve this problem?
I solved it by, yes, by accident finding out that b squared, using the formula, of course, is equal to the identity matrix. And using that, I could just rewrite.
So you are saying that b squared is an identity, is the identity matrix?
Yes, and because it's a odd number that we're powering to, it should just become b. Because if we split it up, we get b squared b.
Okay, so let me follow you because I don't know exactly. So you are saying that you are calculating b squared first. So you say that b is equal to 2a minus I, and your point is to calculate b squared. And yes, these are things accidentally. You need to do this trial and error sometimes, yes. So 2a minus I and then to power 2. Now tell me, am I allowed to use algebraic identity for this?
Yes.
Yes, because 2a and I are the matrices involved and we know that they commute. So this becomes the first one to the 2. 2 times the first one times the second one. A times I is A itself, so I don't write it. And the second one, I squared is also I. So this is the answer. Okay, but now you are saying that B squared is I. Why? Can you tell me? Yes, you are right.
Because we can rewrite A squared as just A, because we know it's idempotent.
Yes, it's an idempotent matrix, so you are right. So this becomes 4a minus 4a. So let me write here, because we know that a squared is equal to a, idempotent. Okay, so this means that I can write it in this form, and then it becomes plus I, and as you see, you are completely right. These two are gone. I get b squared is equal to I. So we learned that b squared is I. Okay. So now, how should I continue to b5? What is your opinion about b5 now?
I would take the left-hand side and split that up into b squared, b squared. Or you can do it faster even. You can do b squared to the squared.
Exactly, exactly. So b5, I would prefer to write it in that way. B squared squared multiplied by b. But b squared is just I, so this becomes equal to I squared times b, but I squared is I times b is b. So that's it. We learned that b to the 5 is equal to b. What can we say about a to the 5?
It should be A.
It should be a, but is it?
Yes.
Why?
By rules we proved previously, but because it's idempotent.
Yes, idempotent. If you want to start everything from scratch, you know, but I think it's better to know these theorems and statements. So if you remember, I told you that if I have an idempotent matrix, we showed by mathematical induction that not only the second power becomes A itself, any power becomes A itself. If you know that A squared is A, so yeah, be happy because any power of that matrix is equal to itself. So I would say that A is idempotent so this means that A to the 5 is equal to A itself. And then we are done, yes, because the left hand side is equal to a to the 5 plus b to the 5, but instead of a to the 5 I am allowed to put a, and instead of b to the 5 I put b, and this becomes equal to the right hand side. I don't know how, yeah, we can, I think we can also, I don't know if you have already solved number 4, we can start solving it. Otherwise, I don't want to spoil the problem. I want to keep it for you. You can think about that problem. Any one of you solve this number 4?
I think I've solved it.
May you elaborate your solution?
Since a is equal to 2b squared minus 3i, I simply replaced all the a's with that identity.
Okay.
Then simplify.
It worked. So what is the answer at the end you got?
I got the zero matrix.
Yeah, I think the answer is right. Yes, so we have enough time to do that. But I think you started doing some algebra, yes? But is there any other way to do it? I would say yes. From my experience, I would say you are completely right. What you said that instead of every b that you see here, every a that you see here, you can use this rule. But let me do it in a slightly different way. Of course, that's your method is completely acceptable as well. So what I do, I will multiply both sides to b. Let me write it in this way: b multiplied by a multiplied by b. So here I mean that I am multiplying by b from the left, I'm multiplying b from the right. Okay, so what happens, by the way, if I multiply both sides of this equality by b from the left, it becomes BA is equal to B times 2B squared minus 3i. And if I continue, it becomes 2B cubed minus 3B. If I multiply both sides of the same equality by B, but this time from the right, this gives me AB is equal to 2B squared minus 3i multiplied by B. And if I calculate this, it becomes 2b cubed again minus 3i times b, which is exactly 3b as well. So what is the conclusion? Can you tell me now? What is the conclusion for this calculation regarding this and that? You see, both of them are equal. So actually, this was an indirect way to show that these matrices are commuting matrices. Now that I know that these are commuting matrices, I can treat them as numbers. Everything is like numbers. And of course, it is completely clear a to the power of 2b as a number, it doesn't make it, there is no difference between this and that, yes, because they are the same numbers. What is the difference? So I know that matrix A and B commute by this calculation. So I can immediately conclude that this matrix is definitely equal to 0. Yes, because we know associativity is distribution, everything is valid, only we lose commutativity. Now we guaranteed commutativity is also the same. So there is no difference between matrix algebra here and number algebra. If I give you these as numbers, it is completely evident that this is equal to. So for example, you can write you can write immediately. This is a to the power of 3, b to the power of 3. Yes, and that's also the same thing if they are numbers. So then what you said is completely correct. What I don't know, might be you have done a little bit more involved algebra, but this is also one way to do that. So the answer would be the 0 matrix. Okay, so there is one problem left. That's actually a nice problem. Let me keep it for the next week and you can work on it yourself. So if you don't mind, I will end. Yes, thank you.